In these last two videos, we're going to look at polar equations and graphs. We are going to break it up into two just to keep these videos a nice, reasonable length. But let's first look at the relationship between a rectangular grid, which is what we have on the left here. That's our XY Cartesian coordinate system, and a polar grid. So a polar grid, we can actually graph rectangular equations and polar equations on both of these. But that polar grid gives these concentric circles of different radius. And when we think about a polar coordinate is written r theta, where that first coordinate just represents the radius or how far away from the origin that point is, and theta represents the angle that we're going to move through to get to that point. So we're going to be practicing graphing polar coordinates on a polar grid in a few moments here. If we're converting between polar coordinates and rectangular coordinates, important to know a few relationships. We've seen these before. We used them in the last video. Cosine theta is equal to x over r, which means that x is equal to r cosine of theta. And sine of theta is equal to y over r, so y is equal to r sine theta. We also might use the Pythagorean theorem, x squared plus y squared equals r squared, and tangent of theta is equal to y over x, given that x is not equal to 0. We might be using all of these different relationships when working between polar coordinates and rectangular coordinates. So first, let's work on plotting some points in a polar coordinate system. Our first point is 230 degrees. So we have a radius of 2. So if we think about this, we're going to plot somewhere along this circle that has a radius of 2. But we're going to plot it at 30 degrees. If you look at our polar coordinate here, and there's different versions of the polar coordinate with more spokes, if you will, to represent different angles. But this one, the one that we have in our notes, is just going to show our quadrantal angles and then multiples of 30 and 60 degrees. So we might still have to graph pi over 4 or 45-degree angles, but those ones are a little bit easier to graph. So 30 degrees, that's this first spoke, and a radius of 2, that puts our point, I'm going to use a different color to make it stand out a little bit more, our point P right there. So we're on that spoke that represents 30 degrees, and we have a radius of 2. So we're 2 units away along that line that represents that 30-degree angle, 2 units away from the origin. Q is the ordered pair -4, 2 pi over 3. So now they're saying that the radius is -4, but we know radius is a length, it cannot be negative. So what that negative implies is a reflection. So what we're going to do here is we're going to start by graphing I'm going to call it Q prime, and that's just going to be +4 and then 2 pi over 3. So we want to find the spoke that corresponds to the angle 2 pi over 3. That's going to be this spoke here. And then we're going to graph a radius of 4. So that point's going to be 1, 2, 3, 4. So there's our Q prime. The fact that our radius is given to us as negative means we're just going to reflect over the origin. So Q is going to be right here. Our last example, point R, is 5 negative pi over 4. So that negative angle of pi over 4 means we're just going to move in the opposite direction, that clockwise direction, pi over 4 units. And then our radius is 5. So 1, 2, 3, 4, 5. That's going to put, let me use the right color. That's going to put point R right there. Give three other pairs of polar coordinates for the point P, which is 140 degrees. So let's start by sketching where point P is. So 140 degrees, that's going to be in our second quadrant. It's not going to be on any of these pretty spokes because it's not an angle from our unit circle. But if the negative x-axis is 180 and this is 30, so that's 150. So 140 degrees is, I don't know, somewhere about there. And we have a radius of 3. So we're going to go 1, 2, 3. And plot our point P. Now what we want to try to do is figure out three other polar coordinates that end at that same point. So one way we could do this is by keeping that radius of 3. I'm going to call this P1. Keeping a radius of 3, but instead of going 140, excuse me, rather than going 140 degrees in that counterclockwise, what would it be if we went the other direction? So let's do 360. Well, the other direction would be going here, measuring this way, and it's negative. So it's going to be that negative angle of 360 minus 140 degrees, because we want to go that clockwise direction. So that gives us 3, and then 360 minus 140 is 220, so that's negative 220 degrees. Okay. Another point, P2. Well, let's think about the reflection of P. So let's go P prime over here, just reflecting it over that, the origin. That reflection just makes our radius negative. So if I do this angle and make my radius negative, what it will do is I'll go to that angle, but then I'll reflect over the origin, landing at P. So that angle between the x-axis and P prime, let's think about what we know about P. P was 140 degrees, so the reference angle between P, or the reference angle for P, is 50 degrees. So we know this is 50 degrees, which means this is also 50 degrees. But since we're measuring it in a clockwise fashion, it's negative 50 degrees. Now that last, or another angle that we can use, is still using that P prime, but rather than thinking about it as a negative angle measured clockwise, what would be the angle measure from P, or from our positive x-axis all the way to P prime, measured counterclockwise? We know from the positive x-axis to P, that's 140 degrees. And then to get to P prime, that's another 180 degrees. Since we're going to need to reflect back to get P, our radius is going to be negative, and it's going to be 140 degrees plus 180 degrees, or negative 3 and 320 degrees. So all three, or really 4 of these ordered pairs, including the one that was given, all land at that same point P. Okay, in the next example, we're going to do a similar exercise. Now we're only giving 2 pairs of polar coordinates, but we want the angles to be between 0 and 360 degrees. So we're not going to include negative angles. All right, so we're given a rectangular ordered pair, negative 1, 1. So we need to figure out what R is, because that's the first value in all of these coordinates. r squared is equal to -1 squared plus 1 squared. We're just using the Pythagorean theorem here. R squared is equal to 2, and r is equal to the square root of 2. Now, because the legs are the same length, we can derive that the reference angle for r, or for this point -1, 1, is 45 degrees, which means that the measure of our angle starting at our positive x-axis is going to be 180 minus 45, or 135 degrees. So 1 point is going to be the square root of 2, 145 degrees. Now, the other angle we're going to look at, or the other point we're going to consider, is that reflected angle. So we want to consider the angle to get to this point, and then we're going to make our radius negative. So our second point is going to be negative square root of 2. And then this angle is going to be 360 degrees minus 45. Again, using that reference angle of 45 degrees, which is 315 degrees. Given a rectangular equation, so that's an equation in terms of x and y, give the equivalent polar equation. Our equivalent polar equation is going to be an r equals, so solve for r. And sketch it on the graph. And then we're going to use Desmos to take a look at this just to see that it did work. We're going to be going back and forth between Desmos again in this video. So we're starting with y equals x minus 3. We're going to use those relationships we saw at the beginning. Y is equal to r sine of x. I'm sorry, r sine of theta. And x is going to be r cosine of theta. So we're just going to substitute those in. Now we want to solve for r. So we're going to combine both of our r terms on one side. R sine theta minus r cosine theta equals -3. Factor out r. So r times sine theta minus cosine theta equals -3. And now to get r by itself, we're going to divide both sides by sine theta minus cosine theta. So we have our polar equation, r equals -3 divided by sine theta minus cosine theta. All right, so looking at Desmos, we have our traditional Cartesian coordinate system. If we use our settings tool, we can actually change between a rectangular coordinate system and a polar grid. So we're going to show that polar grid here. But notice the scale on our x and y axis hasn't changed, so we could still plot a normal point. If you're following my cursor, 2, 2 is going to be somewhere like here. But so what we want to do is we want to type in those two equations. So y equals x minus 3. So there's that graph, our y-intercept of -3 and x-intercept of +3 in terms of x and y, graphed on this polar grid. But now what I want to show is our new equation in terms in that polar form. So we want to make sure we use the correct variables. R equals -3 divided by sine theta minus cosine theta. And if you look, that's the graph in purple, and it lies right on top of that original graph. So this polar equation is still representing a linear equation. All right, let's go through one more. X squared plus y squared equals 4. A quick review. The equation of a circle is x minus h squared plus y minus k squared equals r squared, with a center at the point hk and a radius r. So looking at our equation, x squared plus y squared equals 4, this is the equation of a circle centered at the origin with a radius of 2. So this is just a circle of radius, or r is equal to 2. And that is our polar equation. Very nice, very straightforward. But we may not recognize that right away. So we're going to use that same technique that we used on that the last example, substituting in our sine theta and our cosine theta. So x squared, that's going to be r cosine theta squared, plus y squared is going to be r sine theta, equals 4. R cosine theta squared is r squared times cosine squared theta, plus r squared times sine squared theta, equals 4. And both of these have a factor of r squared, so we're going to factor that out. R squared times cosine squared theta plus sine squared theta equals 4. And if you recall our Pythagorean identity, sine squared theta plus cosine squared theta equals 1. So this is r squared equals 4, or r equals 2. So we ended up with that same polar equation of r equals 2. So back to Desmos, let me clear out my previous two equations and let's type these new equations in. So we have x squared plus y squared equals 4. There's our circle of radius 2. And then we're going to type r equals 2. That's our polar equation. Same exact graph. For each rectangular equation, give the equivalent polar equation. Y equals x squared. We know that this is a parabola, but let's see what this looks like in polar form. Y is r sine theta, x is r cosine theta, and this is being squared. So we have r sine theta equals r squared times cosine squared theta. And start solving for r, we want to start by dividing both sides by r. So then we get sine theta is equal to r times cosine squared theta. And now to isolate r, we're going to divide both sides by cosine squared theta. So we have r is equal to sine theta divided by cosine squared theta. And we'll go through the second example before shifting over to Desmos and verifying both of these examples on the graph. Our second example, x plus 1 squared plus y squared equals 1. So thinking about that equation of a circle, this is a circle with center -1, 0, and a radius of 1. Again, if you don't necessarily recall this or observe this right away, that's not the end of the world. But hopefully now that we've gone through it, it is starting to jog your memory. So before we start substituting in those r sine theta and r cosine thetas, let's go ahead and FOIL out that x plus 1 squared. Dealing with r cosine thetas and trying to FOIL that out, it's going to get a little bit trickier. It's going to be easier to work with our rectangular coordinates while we're starting to simplify this. So this is x plus 1 times x plus 1 plus y squared equals 1. And when we FOIL x plus 1 times x plus 1, we're going to get x squared plus 2x plus 1 plus y squared, which is equal to 1. Now I'm going to rearrange the terms on the left. So x squared plus y squared are together. And I'm going to do that because I know that x squared plus y squared is r squared. X is going to be r cosine theta. And while I'm here, I'm going to go ahead and subtract 1 from both sides. So this is now equal to 0. I'm going to move one of these terms to the other side of the equation. So r squared equals negative 2r cosine theta, so that I can now divide both sides by r, by one factor of r. So we get that r is equal to negative 2 cosine theta. So let's take a look at what these two examples look like in Desmos. All right, so that first example was y equals x squared. There's that parabola. Now, when we converted this to polar form, we got r is equal to sine of theta divided by cosine squared theta. And we see that that also yields the same parabola. In our second example, we had x plus 1 squared plus y squared equals 4. No, I'm sorry, equals 1. Oh, typo there. That should be a plus. There's that circle centered at negative 1, 0 with a radius of 1. Our polar equation was r equals negative 2 cosine theta. And that equation matches that graph.